In this video, we're going to learn about torque and rotational statics. The definition of a rotation is when all points on an object move in a circle around an axis, or you can call it a pivot, which is within the object. Key terms there is within the object. In a rotation, the axis is somewhere inside the object, whereas with a revolution, it's outside the object. So for example, if you have a rotating turntable, like a record player, the rotating turntable moves about some axis that's in the center of it. A point on the turntable moves in a circle around that axis. The turntable as a whole doesn't go anywhere. It's still in the same spot it was when you started rotating it, but a point on the turntable moves in a circle around the axis. Another example would be opening a doorway. The hinge, in this case, is your axis. A point on the door would move in a circle around the hinge. It's not necessary to move in a complete circle to be considered a rotation. Part of a circle will suffice. So in order to understand some rotation and how we make things rotate, let's review first some rotational quantities. In this example, we're going to choose to rotate counterclockwise. So there's a point on the object, moves through some angle theta. So it's rotating, it's going around a circle around the axis in the center. The angle that it makes as it rotates is referred to as the angular displacement. Remember, theta is our symbol for angle, and so delta theta would indicate an angular displacement. Remember, we should measure that in radians. The rate of change in the angle, or the angular displacement, over time is referred to as the angular velocity. We give that symbol the Greek letter omega. That's a lowercase omega. Angular velocity is similar to velocity. Here we would measure this in radians per second. So the definition of angular velocity is change in angular displacement over time. When we have a changing angular velocity, we call that an angular acceleration. We give that the symbol Greek letter alpha, kind of like a fish. And so the angular acceleration, or alpha, is equal to the change in omega over t. Whenever something is rotating counterclockwise, we're going to refer to those quantities as being positive. So if something moves counterclockwise, its displacement is positive, and omega is positive. If it moves counterclockwise and speeds up, then alpha would be positive as well. Now the reason that these rotational quantities are so important is that they're the same for all the objects on the rotating object, all points on the rotating object. The linear quantities are still useful, but not as useful because they're different depending on where you are on the object. For instance, a point farther out on the rotating object has a higher linear velocity than a point near the middle. So how do the linear and angular quantities compare? There's three quantities: displacement, velocity, and acceleration. Linearly, they're defined like this. Displacement's delta x, velocity is delta x over delta t, acceleration is delta v over delta t. The corresponding angular quantities are the angular displacement, or delta theta, which we measure in radians, the angular velocity, omega, which we measure in radians per second, and the angular acceleration, alpha, which we measure in radians per second squared. So this chart might be useful to help us compare those two different quantities. When we want to go from an angular quantity to a linear quantity, the trick is to simply multiply the angular quantity by the radius. And so delta x would be r delta theta. V would be R omega, and A would be R alpha. Now those aren't things that are necessarily going to be provided to you on a formula chart, but there's things that we should understand. In order to make an object rotate, obviously it's going to require a force of some kind. The size, direction, and angle of the force are all still important, just like they were for normal forces, for regular forces, our force unit when we were just making things accelerate forwards, backwards, up and down. With rotating objects, where you put the force is also important. That's the thing that's going to be different. When we draw free body diagrams, we're not going to draw our forces starting at the center anymore. We're going to draw them where they're being applied when the rotational part is important. So for example, suppose you were opening a large door. It has a hinge on the left. It's real big and thick. It could be like a vault door or something like that. If you push it close to the hinge, the door is going to be hard to open. If you push it further out, the door will be easier to open. And if you push the door like that, well, nothing's really going to happen. You're not going to move the door at all, short of like busting it off its hinge or something crazy like that. So even if all three of those forces are exactly the same, they're going to have different effects on the rotation of that door. The different effects we refer to as a torque. So torque is a measure of how well a force causes something to rotate. Depends on the size of the force, the angle, and where it's applied. So here's a object that could possibly be rotating. We'll call that left end the axis of rotation. Here's some force F. The distance between the axis and the force, or the point that the force is applied, we're going to refer to as the moment arm. We're going to give it the symbol R, and it's the perpendicular distance from the axis to the point where the force acts. You could kind of consider that to be a radius, which is why we give it the symbol R. Now be careful. The R won't necessarily be like the radius of an object. It's the distance from the axis to where the force is applied. The farther out we go, as in the greater the moment arm is, then the greater the torque applied is going to be, and the more rotation that force is going to cause. Only the component of a force that is perpendicular to the moment arm actually causes a torque. If it's parallel to the moment arm, kind of like the gray force in the big door example, it's not going to cause any torque. It's not going to cause any rotation. So if we have some force F that's at an angle, what we need to do is figure out what the perpendicular component is. And generally we'll label that F with a subscript perpendicular sign. So in this case, the perpendicular component would be found by using the sine of the angle. The parallel component does not do any torque. So to figure out the magnitude of a torque, which we're going to give the symbol Greek letter tau, lowercase tau, which is kind of like a wavy T, we're simply going to multiply the moment arm by the perpendicular component of the force. If the force is completely perpendicular to the moment arm, then we don't have to do any trig, we just use whatever that force is. If the force is parallel to the moment arm, then it does not exert a torque. The unit for torque is a Newton times a meter. Torque is defined to be positive when it tends to cause a counterclockwise rotation. And we'll see why that is later on. Other possible units for torque are the foot-pound. That's another unit of length by another unit of force. So if you're familiar with torque wrenches in auto shop class or something like that, a foot-pound is just another unit of torque. So, as a simple example, we're going to find the torques exerted by each force on this particular object. Here we're going to have the axis be in the middle, and we're going to apply a 10 Newton force 0.2 meters from the axis. And so the torque caused by that force, multiply the 0.2 by 10, will be 2 newtons times meter. This torque is going to be positive because that force would cause the object to rotate counterclockwise, like that. If we apply another force over here, like a 40 Newton force at a 30-degree angle relative to the bar, 0.25 meters away from the axis, we can find the torque, but we first have to figure out what the perpendicular component of that force is. So we can find that by doing 40 sine 30, which is 20, and then we multiply the 20 by the moment arm, which is 0.25, and we get 5 Newton times meter. Now we're going to make that negative because this force is tending to cause a clockwise rotation. This force makes it want to go like that, which is clockwise. So when you're identifying the direction of a torque, think about whether the force is causing a clockwise rotation or a counterclockwise rotation. Counterclockwise, we're going to make positive. This force would do no torque. It's parallel to the moment arm. If an object is in rotational equilibrium, meaning it's not rotating or it's rotating at a constant velocity, we may see that situation, that means that the torques on the object are balanced. Just like linear equilibrium that the forces were balanced, rotational equilibrium means that the torques are balanced. So suppose we have a bar like this, and we apply a 10 Newton force, 0.5 meters from the axis. And when we apply a second force, upwards as well, 5 newtons, 1 meter from the axis. The torque caused by the first force will be 5 Newton meters. The torque caused by the second force would also be 5 Newton meters, but negative. It's causing a clockwise rotation. And so we can say that those two forces are balancing each other. Now if I reverse the direction of the blue force, now they wouldn't be balancing each other and we'd see this thing spin clockwise. Another way of saying that the torques are balanced is to say that the net torque is 0. And again, net torque just means the sum of the torques. Don't forget to include the sign when you sum up the torques. And so the net torque on this thing will be 5 plus negative 5, which would be 0. Net torque is 0, we know it's in rotational equilibrium, and it's not going to be rotating. Gravity can cause a torque on an object. We always draw the the force due to gravity at the center of mass. The center of mass is kind of a nebulous term for us right now. Typically that's going to be the center of a uniform or symmetric object. We'll learn more about center of mass later in the year. So for example, if we have some uniform rod held at one end, like this, the end that you're holding would be considered the axis. The blue dot represents the center of mass. And so that's where you would draw the force of gravity. So in this situation, the force of gravity is causing a torque about that axis on the left side. It's got some moment arm R, and so the torque would simply be that R times the force of gravity. So if something is not being balanced at its center of mass, then the force of gravity can cause a torque. If an object is in rotational equilibrium, we can choose any axis that we wish to calculate our net torque. We're going to see lots of examples where choosing one particular point to be the axis of rotation is going to be more advantageous and easier to solve for than choosing another one. So, in other words, if something is in rotational equilibrium, that means it has to be in equilibrium at any possible axis point. If an object is in linear equilibrium as well, then the net force still has to be zero as well. That's something that could possibly be useful in problem-solving situations. So let's look at a real quick example. I've got a 2-meter rod, mass 4 kilograms, supported by 2 blocks on either end. And then we stick an 8-kilogram mass at the far right end. And what we want to do with this is figure out the normal force exerted by each block. So a picture might look something like that. Our first step whenever we have forces, and in this case torques, is to draw a free body diagram. Now the difference when we have torques is that we're going to draw the forces at the point of application. Meaning I would draw the force of gravity at the center of mass, the force exerted due to that block at the far right end, the normal force exerted by the right block at the right end, and the normal force exerted by the left block at the left end. So if torque is important, we're going to draw our forces at the point of application. We're next going to write a net torque equation. Just like when we're dealing with forces, we would write a net force equation. Here we're going to write a net torque equation. We're going to choose the axis to be at the far left, meaning that N2 doesn't exert a torque, N1 is 4 meters away, FG is 2 meters away, and FB is 4 meters away. Now we've chosen N1 to exert positive torque because it's tending to rotate it counterclockwise. FG and FB are exerting negative torque because it tends to rotate it clockwise. Now the reason that we choose that is so that N2 goes away in our equation. We're going to set the net torque equal to 0. It's not rotating. And so we get 4N1 minus 2 times 40 minus 4 times 80 equals 0. So doing some arithmetic and some algebra, we would find N1 to be 100 newtons. That should seem to be a reasonable answer. It's less than the sum of the downward forces, but we still have N2 left to find, which will take care of the rest. To find N2, we're going to do the same thing, only this time we're going to set the axis at the far right side. And so I'm going to have negative 4N2. Again, it's negative because it's making it rotate clockwise, plus 2FG. Here the force of gravity is making it rotate counterclockwise. The FB would be exerting no torque. And the same for N1. They're at the point of rotation. They're at our axes. Their R is 0. Again, the net torque is 0. And again, doing some arithmetic, we would get N2 to be 20 newtons. Now there's a way that we can check ourselves. The forces should still be balanced. It's not accelerating up or down or left or right. And so we're just going to check real quick to see if the net force is 0. And so doing a net force equation, it will look something like that. Subbing in the numbers, we would get 0. And so the fact that the forces we calculated give us a net force of 0 tells us that we probably did our torques correctly. So the thing to remember here is that the torque, if something's going to be in rotational equilibrium, must be balanced around all possible axes for it to be in equilibrium. And so if we have something with multiple forces causing torques, we can make the problem solving a little simpler by choosing the most convenient axis of rotation. Here ends the lesson.